So I'm going to go ahead and do 2004 question 4. So this is a possibility for your Chapter 5 exam. All right, so it says, consider this curve given by x squared plus 4y squared equals 7 plus 3x times y. Show that dy over dx equals 3y minus 2x over 8y minus 3x. Okay, the AP exam does this pretty often where you have to verify that something's true, so you have to derive it. And the reason that they do this is so that you can use this later on in the rest of the question without necessarily having to get all of A correct. All right, so part A. So if I'm going to verify that dy over dx equals all of this, I need to differentiate implicitly. And the reason I know that is because I have a 4y squared and a 3x squared, so there isn't really a nice way to isolate y to get it by itself. Okay, so when I differentiate implicitly, I get 2x plus 8y times dy over dx. Remember, whenever you take the derivative of a y, you need to write dy over dx because you're taking it in terms of x, equals 0. And then I have the product rule. So I'm going to have 3x dy over dx plus 3 and then y. Okay, I need to solve for dy over dx. So basically I need to get everything that has dy over dx on the same side. So I'm going to take this one and add it over. Anything that is not dy over dx, I'm going to get to the other side. So I'm going to subtract the 2x. I guess subtract the 3x dy over dx. Okay, so I get 8y dy over dx minus 3x dy over dx equals 3y minus the 2x. Okay, so now I pull the dy over dx out, so I could write this with parentheses with 8y minus 3x in the parentheses, but I'm going to kind of do two steps in one. So I'm going to divide that over anyway, so my numerator was 3y minus 2x, and I'm dividing by the 8y minus 3x. Okay, I have verified this is exactly the same as part A. Okay, part B says, show that there's a point P with x-coordinate 3 at which the line tangent to the curve at P is horizontal. Find the y-coordinate of P. Okay, so this is actually kind of confusing when you first read it. There's a lot of information here, but one thing I noticed is the line tangent is horizontal. Okay, and that's really important. When you see the line tangent is horizontal, that means that you have some kind of curve and you have a horizontal tangent, so your slope is equal to 0. Okay, so that's what we're using. Well, we have slope, dy over dx. We want to show that for this point with x-coordinate 3, we have a 0 slope. Okay, so I want dy over dx to equal 0. Now on your AP exam, you would get 1 point for just writing that. So just knowing that you needed to get dy over dx equals 0. All right, so I have 3y minus 2x over 8y minus 3x equals 0. In order for a fraction to equal 0, the numerator has to be 0. So I do 3y minus 2x equals 0. And I solve. But there's another piece of important information in this problem. It says with x-coordinate 3. If I had not given you that, you would need to find a point that satisfies the initial equation and this equation. So it's a system of equations with x and y. But I was nice in this case, or the problem was nice, and it gave you that the x-coordinate was 3. So I have 2 times 3 equals 3y. So y equals 2 times 3 divided by 3, so it's 2. So that means our point is 3, 2. Okay, that is a point where your slope is equal to 0. But I don't know if 3, 2 is necessarily on the curve. It might have just worked out nicely on this slope thing, but it may not have worked in our original equation. So I always go back and check. So x squared plus 4y squared equals 7 plus 3xy. Because it's asking you, is there a point? Well, it says show that there's a point. So we need to show that this point is actually on the curve. So I get 3 squared plus 4 times 2 squared. I'm seeing if it's equal to, so I usually put like a little question mark, or you can do the left side and the right side separately. 7 plus 3 times 3 times 2. So this is 9 plus 16. 7 plus 3 times 3 is 9, so 18. So 25 equals 25. So yes, 3, 2 is on the curve. And dy over dx there is 3 times 2 minus 2 times 3 over 8 times 2 minus 3 times 3, which is 0 over 16 minus 9, so 7, so it's 0. So the slope is 0. And the only reason I would go back and do this dy over dx thing, plugging it into the entire thing, is because you could have had 0 over 0, which would be bad. So we wanted to verify that it was actually just equals to 0. So it wasn't a hole or anything. Okay, so C. C says find the value of d2y over dx squared. So this means the second derivative of y in terms of x at the point P found in part B. So at this point, so we had 3, 2. We want to find the second derivative. Okay, well, we were given the first derivative. So we were given that the first derivative is equal to 3y minus 2x over 8y minus 3x. And that's one of the reasons that they went ahead and said, show that this is true. That's why they gave you that derivative, because you're going to use it throughout this problem. Okay, so d2y over dx squared. So I have to use the quotient rule. So I would say low d high minus high d low. So low d high is going to be 3 dy over dx minus 2. And then minus high d low. So high is 3y minus 2x. D low is 8 dy over dx minus 3. All over the square of what's below. Okay, we're evaluating it at a certain point. So our point was 3, 2. So this means evaluate at that certain point. So everywhere I have an x, I'm going to put 3. Everywhere I have a 2, I'm going to put, or everywhere I have a y, I'm going to put 2. And then what about the dy over dx? So that's at a particular point, and at our point, our slope was 0. So we're going to plug in 0 here. Okay, so I get 8 times 2 minus 3 times 3. That's the first part. I have 0, so multiplied by negative 2. Minus 3 times 2 minus 2 times 3. Multiplied by 0, so I just have negative 3. All over 8 times 2 minus 3 times 3 squared. So simplify. So 16 minus 9, all times negative 2, minus 6 minus 6, so not minus 6 minus 6, so 6 minus 6, right? All of that equals 0. So times negative 3 would still be 0. So that's kind of nice. It wipes out half of our problem there. Divided by 16 minus 9, so 7 squared. So 16 minus 9 is 7 times negative 2. So I'm going to write it as 7 times negative 2, and instead of multiplying it out and then reducing, I'm just going to divide by 7 on the top and bottom, so I get negative 2 sevenths. So that is the value of the second derivative. Okay. What's important about that is that I notice it's negative, so that means it's concave down. At 3, 2. Okay, and be very specific. So what is concave down? The original, so the curve. So the original curve is concave down. Okay. All right, so does the curve have a local max, a local min, or neither at point P? Justify your answer. So what we know is that our curve, I'm just going to write the curve. The curve is concave down, and dy over dx is equal to 0 at 3, 2. Okay, so what that means is that we have concave down, and the slope is 0, so there is a maximum. So this is using what we call the second derivative test. So you can call it that, or you could just list those two things and say, therefore. So therefore, there is a max at 3, 2. Or you can call it point P, since they refer to it as point P. So this is by the second derivative test. So like I said, you don't actually need to write it by the second derivative test because you have used it here. So you said the first derivative is equal to 0, second derivative was negative. Therefore, there's a max at 3, 2.